Hello and welcome back to another video. In this problem, we're asked to prove that the equation has at least one real root. The natural log of x is equal to 3 minus 2x. So the first step is to get everything on one side. Because what that does is this cancels out, and we're left with the natural log of x plus 2x minus 3 is equal to 0. We're going to call this f of x, and we're looking for values of x such that f of x is equal to 0. And this isn't an equation we can directly solve, so we're going to use the intermediate value theorem. And so before we do that, first of all, this should be an x. We can say that ln of x, 2x, and negative 3, right? If we take it like this and this, we have a logarithmic function and a polynomial. And we can say by theorem 7 that these are continuous over their domains. So for 2x minus 3, that's all real numbers. For ln of x, that is x greater than 0. Therefore, their sum by theorem 4 states that the only restrictions on continuity is that the individual restrictions based off of ln of x and 2x minus 3, which is only x greater than 0. So we know that our function f of x is continuous for x is greater than 0. So for any x is equal to a and b, if f of a is less than 0 and f of b is greater than 0, we know there is a root on the interval from a to b. Why? Well, if we imagine our function up here, at a we have a positive number, at b we have a negative number, or like vice versa. If the function is continuous, we know that it has to hit the x-axis at some point going from positive to negative. Right? The only way to get around this would be to like skip or jump or go off to infinity, and it can't do that because it's a continuous function. So it must have a root if we're going from positive to negative, or like negative to positive would be the same thing. So what we have to do is we have to find an interval where one end is positive and one end is negative. So we can plug in values for x and get the solution. So plugging in 0 wouldn't work because you can't take the natural log of 0. Again, we have to do positive values only. F of 1 is ln of 1 plus 2 times 1 minus 3. That is negative 1. F of 2 is ln of 2 plus 2 times 2 minus 3. That's going to be equal to 1.69. And therefore, f of 1 is less than 0. F of 2 is greater than 0. F is continuous over the interval. Therefore, f has a root on the interval from 1 to 2 by the intermediate value theorem. In part B, we're asked to reduce this interval from a length of 1 to a length of 0.01. And so what we can imagine is we have this interval here, right, from 1 to 2. And we know at 1, the function is negative, and at 2, the function is positive. So we have to reduce this in order to get a smaller interval that still has negative and positive ends. So the easiest thing to do is to cut it in half, 1.5. This is ln of 1.5 plus 2 times 1.5 minus 3. That is going to be 0.4. So 1.5 is also positive. And we can say that it's a lot closer to 1.5 than 1, right? Since f of 1 is closer, f of 1.5 is closer to 0 than f of 1 is. So let's try values closer to 1.5. So f of 1.4 is ln of 1.4 plus 2 times 1.4 minus 3. This is 0.136. So f of 1.4 is still positive, but we're getting very, very close. So maybe try f of 1.35. This is ln of 1.35 plus 2 times 1.35 minus 3. And this is 0.0001. So this is very, very close, 1.35, but it's still positive. So we just have to go, if we're looking for an interval of length 0.01, let's go 0.001 less to 1.34. This is the natural log of 1.34 plus 2 times 1.34 minus 3, and this is equal to negative 0.027, and therefore 1.34 is negative. So we have found an interval for which the first end of the interval is negative and the second is positive. Therefore, by the intermediate value theorem, we can say that on the interval from 1.34 to 1.35, since the function is continuous over that interval, we know that for it to go from positive to negative, it must have a root somewhere on the interval.